welcome to this session. My name is Wycliffe, and in this video I want to share with you how you can understand the concept of scale when doing extraction of data from Google Earth Engine. Normally, we are told to change the scale of extraction or scale parameter when obtaining data from Google Earth Engine, especially to make it a bigger number, like 1,000 or so, depending on how much area or region of interest we want to extract data from, so that we don't run into memory problem. But then how does that affect, for example, the quality of data you're getting or the representativeness of the data you're getting for your region of interest, right? So let's dive into R and see how this can be done. Okay, so in R, we will start by loading the library RGEE, and then we will go to another library, which is called MapEdit. This is the library which will help us to draw a region of interest. And then we will also load a library called ggplot because we want to have some line plot of how the value of extracted changes when we change scale, for example. And as usual, we start by initializing our RGEE session so that we are connected to the Google Earth Engine. Okay, so we will use draw features function from MapEdit, and then we convert the SF object created to an Earth Engine object. For my region of interest, as many of you might already know, I'm super interested in tea. So I will select a region which is inside a tea growing region. So let's get into some region, maybe this region here. I will take this drawing toolbar or tool and then drag it across my region of interest, and then maybe that's reasonably fine because I'll change scales. I'll not go into 10 kilometers or so. So this is just a distance of maybe 3 or so kilometers. So my extraction scale will go up to a maximum of maybe 200 meters. So that's fine. Okay, so once we have our region of interest as an Earth Engine object, if you check ROI, you realize that it's an Earth Engine object, which is a feature collection. That feature collection we can use to do the clipping, cropping, extraction, and everything from we want to extract within that region from Google Earth Engine. All right, so let's get our Sentinel-2 image. So our Sentinel-2 image is an image collection. So we say image collection, and then we go for dataset, and then we obtain it as S2SR, that one harmonized. I can expand this a bit. Of course, you can also get it from the image ID, which you pick as a snippet from Google Earth Engine code editor. But in R, you can simply chain it like that. Okay, but this image is normally compromised by clouds because we are going to maybe create an ndvi. So we can get also the cloud score plus data, which we can use to mask out cloudy pixels. So this one here. For that, we can look for the start date. We can provide our start date. Let's say we want it for the month of October and November. So we can say 2025, October 1st. That is the start date. And then the end date is 2025, October, say whichever, November, maybe November 1st. November 1st. Let's end at that. That is the extraction window. So to get our ndvi, can say our ndvi, we get our Sentinel-2 image, and then we filter bounds. So we filter only the images that coincide with our region of interest. After filtering for the region of interest, then we filter date. The date we are filtering is between the start date and end date. So we only need images that coincided with that period. Once that is done, then we can now link our cloud score band or collection. So we say link collection. We use link collection function, and then the collection we are linking is CS plus, and in CS plus there is the CS band which help us to remove clouds. Okay. In removing cloud, we just map a function over our images, and the function takes each image. After picking image, then you decide which one among the bands is the quality band or the band for masking. So we use select function, and the band we are selecting is CS because we have linked it to our Sentinel-2. So it's already there in every image, okay? So after selecting the quality assessment band, we can then update our mask. So we say our image is the original image, but we update mask, whereby the quality assessment band gives us a value which is greater than 0.6. Okay, so that's a clean image now. Then we get our ndvi, which is the image. We can just call the image and then say normalized difference. And to this normalized difference function, we just provide the two bands of interest. And near infrared is band 8 in Sentinel-2, and then the red band is band 4. After that, we rename the product or the output as ndvi. Okay, so that will give us the ndvi image. So the next thing is to get the median for that period. It's 1 month, October to November 1st. So we get the median, and then to that median, we can clip to our region of interest. Okay, just like that. So that gives us median ndvi for our period within our region of interest. So if you check ndvi, it's an image, and if you print it, you will see a single or one band with metadata information about the band. Okay, so after we get our ndvi, then we can even visualize it if you want to. You can expand this region. Then we send our map $center object, and the Earth Engine object is the region of interest, and the zoom level is maybe 12, right? Okay. After setting the, let me expand this a bit. After setting the map center and the zoom level, we can then add layer. Not sure why this is starting in. Okay. We add layer, and that engine object we are adding is our ndvi object, which we created up here. And then after adding this, we can also provide some visualization parameters, which in R is provided as a list. And in this list, we can say pick only where the minimum is 0. ndvi ranges from -1 to +1, but let's clip it at 0 to 1 because this is a T-growing region. So ndvis of -1 are very rare. Below 0 is very rare, except maybe if you go to water bodies, okay? Or a dam or some pool of water or very dry region in this area, okay? Then we can provide color palette, low values as red, and then maybe dark green for super healthy vegetation, okay? Yeah, we already clipped it to the region of interest, so that should be nice because I thought I had not clipped it. So yeah, that's the normalized difference vegetation index. Most farms were healthy. This probably was replanted or pruned or something happened. Okay, so we want to see how change in extraction scale affects the data we get. For example, if we want to reduce region here and get the median ndvi, right? If we want to reduce region here and get the mean ndvi, let me just do that quick. We can say ndvi $ reduce region, and then the reducer we can say is EE $reducer $mean, for example. Okay. Then we provide a scale of say 10 meters. Okay, this gives us a dictionary, then we can get information from the dictionary. So reducer provide geometry. Oh, the region of interest, we did not provide the geometry. So here. So our geometry is region of interest. Okay. So that gives us an ndvi, the median or the mean ndvi in this region to be 0.76. What about if we change the scale? Let's say the scale now is 100 or something. Let's say 100. We now get 77, a different value. What if we change the scale to 30? 7686. So 7678, a different value. So changing the scale of extraction affects the value you are getting. So which of these is the median or the mean ndvi of this location, right? Normally we go with that of the standard of the scale of the image. Like if it is 10-meter resolution, then that is the best you can get. All these other scales you are providing as 1,000 kilometers or 100, a scale, whichever scale you provide, which is not the native scale of the image, will degrade the quality of the final output in some way, because it will have to expand, first of all, aggregate the pixels to that scale, and then give you the final extraction. So let's try this and see different scales. So we can provide so many scales. Those ones have just tried 3. So we can create a sequence of numbers, maybe between 10 to 200. You can create even above that if you want. And they are increasing by 10. So these are just 200 numbers, or a vector of 200, 10 to 200 increasing by 10. Okay, yeah. So these are just 20 numbers, right? So we want to try all those scales, run for all those scales. So in R, we can simply do a loop. So we can say, first of all, we create an empty vector to carry the values. So this is an empty vector. Let me call it ndvi. It's null. Its value is null. It's just a vector which is empty. So C and empty, there is nothing inside. Okay. Then we can say for item in the length or sec along in the length of scales, that is from the ith item to the 10th item, the 20th item in that list, in that vector, extract some result. So take the ndvi image and then reduce region for it. So we will reduce region, and the reducer is say mean, $mean, and then the geometry around which we want to do the reduction is our region of interest, and then the scale. This is now important. We are now not using a scale of 10 or 20 or something, but we are picking scale from the scales vector, the ith scale, okay? Then after getting the ith scale, we will need to get information because it will be returned as a dictionary. And then after getting the information, then we can add it to the empty vector. We can populate the vector we created up here. So ndvi values will be picking the ith output. Of the ith output, we'll be picking the result. And this result, I don't know if we can still print the other one. This one, you can see it has got the ndvi item, which has this value. So from this result, we pick the ndvi. Yeah, that is when we just get the value itself. Okay, so we can run that. We can loop through the numbers. So 20 values will be returned in these ndvi values. Okay, so to visualize this, these numbers that will be produced, they're still running. Reduction is still, it's finished. So you can just check like this and see all these values corresponding to each of the scale level. So they are all different values, okay? So let us then create a data frame of these values and the scales so that we can use ggplot to visualize them. So we can simply say df is a data frame, and the data frame gets the column scale, which comes from scales, and it gets the column ndvi, which comes from ndvi values, which we have just created. So it's just a simple data frame of 2 columns, right? Where on the one axis is the scale, 10, 20, 30 up to 200, and on the other axis is the ndvi value, okay? Then now we can generate the plot, which is a ggplot, and in the ggplot we provide it with the data frame, and for the visualization, ggplot data frame, aesthetic. For the aesthetics, we will take X. On the X-axis, we will put scale. Scale, it is not scales, it is scale. And then on the Y-axis, we can put ndvi. And then we can use a geom line just to see how that changes. We can use geom box plot or geom something. And we can also add geom point at the joints toward the intersection. Many things you can set the minimal if you want. A lot of things that you can put there. Okay. I mean, just to confirm that ndvi values change depending on scale. So this does not need to show any trend of increasing or decreasing. It depends on the neighborhood of that region you're extracting with it. So that when these values are aggregated, then you notice you get some changes. So the best value would be the one which uses the scale of that, the native scale of the image, and you can see how varying it can change the actual value extracted. If you use different scale, it can change. But normally this is not a big problem if you are working on a very, very large area. There is always that compromise between the quality of data and the scale within which you are doing the projection, the extraction, okay? So finally, we can compare the 2 images, because what happens when the scale of an image is reduced, right? So we can say the projection at the native 10 meter, what is the projection of this image? So we have our ndvi, and then we can get its projection, this one, okay? That will give us the projection of our image. After getting the projection, we can create our ndvi at 10 meters. 10 meters, which is basically the ndvi, but clipped to our region of interest. Of course, we had already clipped our region of interest, so that's not so important. But we can create the ndvi at 200 meters, right? Because we've grabbed the projection. So this will be the ndvi at 10 meters, which is basically the ndvi, and then we reproject, okay? So how do we reproject? In reprojecting, we provide the coordinate reference system, which is the projection at 10 meters. We just extracted from the ndvi, and then the scale is now what we vary. Let's say we now project it to 200 meters, the original image, okay? Then we can now visualize the 2 images. So our map, we had already centered it, so we can just add layer and the Earth Engine object. For example, we can start with the ndvi at 10, and then we can provide visualization parameters. And the visualization parameters, we can provide as a list in which we have a minimum of 0 and a maximum of 1 and a palette of, let's say, red, green, red, yellow, green, red, yellow, and green. Okay. And that's our ndvi. You can give the name or no problem at all. So that's the same ndvi we had before, but now we added another ndvi. We will use the par, and then we add the ndvi at 200. Okay. So we just change this to 200 and everything else remain the same. Now you can see the difference between the two. It is just exactly the same image, but at different resolutions. Now the data extracted from this and the data extracted from this are of course different. This is now reduced to a coarser resolution. Cells have been aggregated to say have been aggregated to 200 meters, but here they are fine at 10-meter resolution. So if you extract at a lower scale, that is how you lose information. You can see at the edges, the 200-meter resolution extends outside the boundary of the original one because cells are being aggregated to attain the scale indicated by the user. Okay, so thank you so much. That's what I wanted to share with you. Scale is important when extracting data, and you should know how it affects the final output or the final data you are extracting. It can lower, it can increase, it varies depending on the aggregation or the scale you use and depending on the scale you use. If you use the native scale, you get the best possible out of the data. If you use different scale, then you are lowering or adjusting the quality of the data. Okay, thank you so much. If you find this video useful, please share it, like it, and also give it to your friends who are interested in these kinds of analysis or understanding. And then remember to cite all the data sources you use as well as the packages you use. The link to this code I leave in the description section of this video, and you are free to go to my GitHub page and grab it and use it for your own project. Thank you and happy coding.